I actually, before I was full-time in physics, I was a science writer, and I was employed as a freelancer writing about the research at IBM, Thomas J. Watson, which was their principal, still is their principal research facility in New York. And I could see by what they were asking me to write about this very rapid evolution uh, in the course of the 90s, because some of my first articles were actually astrophysics. There was a researcher who was studying the development of galaxies. So this was
At IBM?
at IBM, pure basic research that they were funding because they did feel that, basic research would someday lead to uh, applied research. So as the years went by, as I say, this was pretty rapid during the 80s and 90s. Um, First, they stopped the basic research, and then fewer and fewer of the applied research, the development of new semiconductors, new semiconductor technology, didn't die off entirely, but it became less and less, and more of the articles were strictly about software development. So I could see this go over a very rapid period. So obviously, all of these tend to break the idea that we learn, that as we learn basic uh, science, we apply it to applied technology, and then we can apply that applied technology both to improving life and to developing new scientific instruments.
Mm.
But I do want to, at some point, get to why we're talking about Big Bang as a myth and not science.
Yeah, let's get there. I definitely want to make sure that we understand the evolution of plasma cosmology across the 20th century first. But one quick question. Was the IBM research related to the galaxy filament simulations that are in your book?
No, I'm trying to remember the exact research I had written about. Um, yeah, I think I do. This was Elman, a pair of scientists. Yeah, I'm sorry, I forget his wife's name, but you should look it up.
It was a
Uh,
couple.
yeah, they were a couple of astrophysicists. So the basic question is, and this is a problem that is throughout conventional cosmology. If you ignore electromagnetism, you don't get results from gravity that correspond to observation. So the key question is, you look at galaxies like our own. It's easier to look at other galaxies because we're not inside them. And they're these beautiful pinwheels. They're these spiral disks, with the disk being much thinner, 10 times thinner than it is across. And people realized very early on, I don't know whether this was, yeah, this was at the start of computer simulation, that gravity would never form this, absolutely never form disks with these spirals for two reasons. One is if you somehow impose the spirals, gravity would never create the spirals. If you somehow compose, impose the spirals at a certain time in your simulations, gravity destroys them. It wipes them out because in order to maintain a spiral, the velocity has to increase linearly with distance from the center. But as Kepler pointed out centuries ago, and has never changed since, with gravitation, the velocity uh, increases as the square root of the distance. So if you have a mass, then Newton's formula is G, universal gravitational constant, times mass equals v squared r. So as r decreases around the same mass, like sun or the center of or a galaxy, V will decrease as the square root. So that means that the outer edges of this spiral will fall further and further behind. And as the astrophysicists say, it's the winding up problem. Spiral will look more and more and more, have more and more winds, and then it will completely get erased. Same thing with the disk. The disk, while a stable configuration in the short term, it starts to get wobbles. And eventually it becomes a fat disk, not a thin disk. So Alma-Greens were studying this observationally. They were studying velocity, how velocity varied. I'm not sure how much they were getting into the question of what's the solution. So this was one of the early justifications for dark matter. If you say dark matter does not interact with itself, it's just like fairy dust. You can describe it as any way you want. Fairy dust is green, it's blue, it's invisible and blue. If it doesn't interact with itself, it won't settle into even approximately a disk. It will be a sphere. And if we arbitrarily make the sphere more massive than the disk, we can stabilize the disk. You still can't stabilize the spiral, but at least you've got the disk.
Our videos come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy in a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks.